Okay. Yes, I welcome you all for this class on signals and systems. First of all, this is the session what I'm taking now for module number 3. Okay. So let me start sharing my screen now. Okay. Okay. So now I'm talking about module number 3. Okay. So which is entirely related to Fourier analysis. Okay. So the module number 3 is generally called as continuous time Fourier transforms, but let me generalize it as Fourier analysis. Okay. So I'm talking about continuous time Fourier transforms. Okay. So I'm talking about continuous time Fourier transforms. Okay. So it is called as CTFT. But when I proceed to my lecture in today's class, I'm going to concentrate more about continuous time Fourier series and later on the continuous time Fourier transforms and certain properties which are related to both of them. Okay. And we are going to have some application level problems and we are going to have some slightly problems related to direct solving method. Okay, so that's generally using the given formulae. Okay, one or two formulae will be there. So let us discuss in detail about these modules. Okay, so first and the foremost thing is the introduction aspect to the Fourier analysis. Okay, so module number 3 I'll be covering regarding the continuous time Fourier transforms. So first thing I'll be discussing about the definition. Okay, so how you are going to define the Fourier transforms, and just before Fourier transforms I will be covering about the Fourier series there. Okay, so next one it is regarding the properties related to Fourier series. Okay, properties related to Fourier series, FS. Okay, so meanwhile I'll be using these short forms. Okay, so you need to be clear about this short forms, that is CTFS. Okay, CTFS, which means continuous time Fourier series. Okay, so next we are going to discuss about two aspects there, that is the periodic nature of it. Okay, periodic signal and the non-periodic nature. Okay, when we are going to use the Fourier transforms, okay, when we are not going to use the Fourier series and so on. Okay, so we are going to analyze such things, and along with that we are going to model a given circuit. Okay, so we are going to model a given circuit using the, yes, so when I talk about continuous time system, what type of equations it will be? Yeah, what type of equations? Am I using the difference equations or the differential equations to model continuous time systems? Okay, continuous time signals. Okay, yes, can anyone unmute themselves and they can do let me know? Continuous signal, I have a continuous signal, say x of t. Okay, so this continuous time signal, say x of t, how you are going to model it? You are going to model it by what type of equations?
Differential.
Wonderful. Okay, so I appreciate that. That is using the differential equations I'm going to model a given continuous time signal. Okay, you have a continuous time system, say CT, okay, which is having a continuous time signal, and this continuous time signal can be analyzed with the help of the differential equations. Okay, so you are going to call the differential equations. Okay, so that's how you are going to analyze a given continuous time system. Okay, so it would be very useful for you to analyze using the differential equations. We have already done the natural response and the force response of the system. It would be quite easy for every one of us to analyze the differential equations there. So when I talk about differential equations, one thing I need to be very clear is the input x of t, what type of input, that is x of t, that I'm giving, and the given output that is dependent on the system parameters. So what we had observed in the convolution network is I will be having a linear time invariant system. Okay, so LTI system refers to the linear time invariant system there. Okay, so how did we perform the convolution? So we had y of t and we had the input x of t and we had the convolution operator. Okay, so this star mark refers to the convolution operator. So this convolution operator was used to convolve the h of t. Okay, so convolution is a mathematical operator. Convolve. Okay, so we are going to convolve two signals in order to get the required output, that is y of t. So h of t is the, what is h of t? What is h of t?
Impulse response, sir.
Very good. Okay, so it is the impulse response of the LTI system. Okay, so why it is called as impulse response? Because the input that I'm giving, okay, so this LTI system along with x of t, I'll be having the impulse response that is dependent on the input, that is delta of t. Okay, so with this basics, let me move on to simple applications where we will be generally going ahead with using the Fourier analysis there. Okay, so let me concentrate on three different applications, general applications, which you can see in anywhere. Okay, which you can see anywhere. So first one is a simple electrical network. Okay, so where you would generally come across the h parameters and the y parameters, z parameters, and so on. Okay, so a given electrical network can be modeled using the Fourier analysis. Okay, so along with considering the input, you will be having the electrical network here. So this electrical network, if you analyze it in a mathematical representation, so you can able to model it using the given Fourier analysis. So Fourier analysis is one important tool which you can find it as a wide application in case of any electrical system or an electronic system. Okay, so in case of power electronics, okay, so in case of power electronics, if you come across any like you will be having PWM, that is, any idea what is PWM? Yes, I'm asking a question here. So do you know what do you mean by PWM? Anyone can answer?
Pulse width module.
Very good. Okay, so what you are doing there, so you are varying the pulse width there, right? So pulse width is being modulated using a sinusoidal wave and a triangular wave, and whatever the points that matches. Okay, so there you will be having it, and the pulse width can be varied, like increased or decreased depending on the like the triangular wave, that is the carrier wave there, right? So sinusoidal wave is taken as the reference, and the triangular wave, whatever that is there, so matching those points on the given sinusoidal and the triangular wave, you are going to vary the pulse width there, right? So depending on the spectrum that you are going to get after giving the pulses to the given switches, so in order to analyze that spectra, okay, so spectra is nothing but a wide ranges of harmonics that are being present there. Either it might be a magnitude spectra or a magnitude or amplitude spectra, or you can generally call it as the angle one that is there. Okay, so you are having any complex quantity which can be analyzed by both that is the magnitude and also the angle there. Okay, so in certain ways you are going to analyze the Fourier analysis, which becomes a mathematical tool for analyzing a given system there. Okay, so depending on the parameters that are present there for the electrical network, okay, so x of t will also have certain networks, certain parameters which are associated. It might be the initial condition and so on, and depending on the amplitude of it. And in the electrical network also you will be having the elements RLC or combinations of it. Okay, so depending on the parameters and also the input, so y of t, okay, the output of the system is being recognized there. Okay, so it might be the input might be generally like any periodic function or any periodic function. And if you know the details of the electrical network quite easily, so y of t, the output of the system, can be analyzed. Okay, so second one, okay, when it comes to the communication systems, very important one. Okay, so if you're having your career in the communication systems, you will be having a term called as modulation. Okay, modulated. Okay, so in pulse width modulation, that is PWM, that is with respect to the switches that you are operating, that is the pulses that you are giving to the switch, whether to turn on and turn off. And next one, which is nothing but the modulation there. Okay, so if you have come across two types of modulations, generally what it is? Yes, can anyone just tell me what types of, if you have communication systems, general communication systems, or whatever that you have observed previously, maybe while viewing any channel or something like that, if you are turned on to radio, okay, so you have two types of modulations generally. Yeah, we can have a discussion. Yes, you can unmute yourself and you can talk. Yes, one is the amplitude modulation, correct? Yes, next one, frequency modulation, right? And later on, you'll be having the phase modulation also. Okay, so phase modulation is one thing where you will be having the shifted version of it when it comes to the wave that is being traveling there. So once I talk about this amplitude modulation, the amplitude is being varied here. So amplitude modulation, we call it as an AM wave, right? So such systems are generally having the amplitude being modulated depending on the requirement. Okay, so next you will be having the frequency modulation. So you would have observed we don't have 98.3 AM. Okay, so that is, this amplitude is being varied, and if you have 98.3 FM, okay, that frequency, this frequency channel, whatever that is there, so that is with respect to a radio which is already being occupied. So you can't have a song which is being playing in 94.3 and 98.3 to be the same, just like you will be having the different variations in the frequency range there. Okay, so that frequency range, okay, which will be allotted to that particular channel there, right? So we don't have any such like song or any information which is being shared in 94.3 to be the same in that of 98.3, unless it is a traffic jam or something like that which is there. Okay, so generally speaking, it would be entirely different. Okay, so now certainly you will be having one multiplier system. Okay, so I'll be drawing only the simple system here. So I'll be having the signal which is there, and I'll be having a carrier wave. Okay, so a signal which is there, and I also have a carrier, and I'll be having the output, that is y of t. Okay, so this output is generally called as the modulated output. Okay, so this output is generally called as the modulated output there. So I have a signal and I have a multiplier system that is there, and I have a carrier wave. So this product of both signal and the carrier wave will give me the desired modulated output. Okay, so depending on the requirements of the signal, carrier wave, so all these properties of the modulated output can be analyzed using the Fourier analysis. Okay, so if time permits, okay, I'll give a practical example how in communication systems or in electrical network. Okay, so how the Fourier analysis is being used in case of the communication systems there. And one more thing is your sampling technique. Okay, so what do you generally mean by sampling technique is, so you will be having a continuous time system there, right? So in case of continuous time systems being reduced to the discrete time systems, okay, so in order to like analyze a system, what would be the behavior of it in that particular point of time, you are going to discretize it, right? So you are having a continuous time system like this, I mean continuous time signal like this. So for example, if I want to analyze at this point and this point and this point, okay, so if you can observe quite clearly, the width will be like equal. Okay, so if you want to like set the width to be equal, you're going to have this sampling frequency or a sampled frequency at that particular point of time there. Okay, so this sampling frequency that is there, which will be equal in width, and after that it will be in the integral multiples of it. Okay, so in the same way what we discussed for the periodic signal and the aperiodic signal, in the same manner you will be having a sampling frequency is being set up in order to find the continuous time to the discrete time there. Okay, so that is one thing that you will be really coming across in case of the Fourier analysis. So you are going to analyze it with respect to the continuous time system, and then you are going to reduce it to the discrete time system. Okay, so then you are going to reconstruct the signal of the discrete time after analyzing, and then you are going to have the sampling being done there. Okay, so that's how we are going to analyze a given uh, like a continuous time system in order to analyze it. Okay, so that is where you will be finding out certain things. Okay, so now if I want to talk about the major thing, how a Fourier series is being represented. Okay, so let us discuss about the Fourier series. Okay, so Fourier series representation, so how it is being represented. Okay, so Fourier series representation of continuous time periodic signals. Okay, so Fourier series representation of continuous time periodic signals. Okay, so you will be having a theorem also there, or a corollary, which I want to highlight in the later part of the class. Okay, so now before coming to the major Fourier series representation of it, the continuous time signal, so one simple table what I'm going to draw here. Okay, so it would be quite easy for you to understand. So you will be having the periodic nature of it, first one, and this one is the aperiodic nature or a non-periodic nature. Aperiodic or non-periodic. Okay, so I'll be having the periodic nature of it. First one, you will be having CT, which is the continuous time, and this one will be having a discrete time there. Okay, so first one is the continuous time, and the second one will be the discrete time. So this will be the time property of the signal, which is the continuous time system and the discrete time system there. Okay, so now this periodic and the aperiodic signal, very important table. Okay, so this table where you can keep it in your mind what I'm going to talk here. Okay, so I had already told you in the introduction one itself, so we have Fourier series and Fourier transforms. Okay, so you will be in a dilemma which one to use, when or what type of signal, whether it is a continuous time signal, whether we have to use the periodic or the aperiodic, which one, Fourier series or Fourier transforms, which one to use it. Okay, so this table will be quite easy for you to analyze it. Okay, so any continuous time system which is periodic, okay, I'll take it as A and I'll take it as B here. So if I have a continuous time signal which is periodic, we are going to use the continuous time Fourier series. Okay, FS refers to Fourier. Okay, Fourier series. Okay, so this is one thing that you need to keep in mind. So continuous time and it is periodic. Okay, I have two like classifications of signal, right? So one being the continuous and the discrete time signals, and next one being the periodic and the aperiodic type. Okay, even and odd and certain things are already there. So if I have a signal, what do I need to do? First one, I have to see whether it is a continuous time signal or a discrete time signal. Okay, I have confirmed it as a continuous time signal. So second one, what do I need to do? I need to check whether it is a periodic signal or a aperiodic signal or a non-periodic signal. So from being the continuous time system and it is periodic, we are going to represent it by a Fourier series. Okay, always remember, once it is periodic and continuous time, so we are going to use CTFS. Okay, so which is continuous time Fourier series. Similarly, I have a continuous time signal and I say it is aperiodic. Okay, so it is continuous time Fourier transform, FT, which refers to Fourier transform. Okay, so Fourier transform. Yes, so this is the name of the scientist. Okay, so Fourier, it is Joseph Fourier who found out the certain Fourier transforms. We will be having Hilbert transforms and so on, which is there. Okay, so in the same manner, the scientist's name was Joseph Fourier, who was there. He found out certain mathematical tool which can be used to analyze certain signals. Okay, so next one, which is the discrete time Fourier series, DTFS, and this one is DTFT. Okay, so this is discrete time Fourier series. Okay, discrete time Fourier series. CT and DT refers to discrete time DTFS, which is discrete time and it is periodic. I'll be having the discrete time Fourier series. Discrete time non-periodic, that is discrete time Fourier transform there. Okay, so these are the properties that are being appropriate properties for Fourier representation. Appropriate table, you can just remember this appropriate table for Fourier representation. Fourier representation. Fourier representation. Okay, so we have to keep these things in mind. Okay, so then we can easily analyze the system. Okay, so we will be knowing whether the Fourier series has to be applied or a Fourier transform to be applied. So making use of this table which is there, it would be quite easy for you to analyze whether you will be going for the Fourier series or the Fourier transforms. Okay, so now what we'll be doing here is I'll show you the Fourier series representation of the continuous time signal there. Okay, so let us start. As I already told you, let x of t be the continuous time signal with period t. Okay, so period t, which is periodic in nature, so it is represented analytically. It is represented analytically. It is represented analytically as an infinite series, as an infinite series of complex exponentials. Okay, so here I'm talking about x of t being the complex exponential there. So complex exponentials. Okay, so this x of t can be represented as sigma k equals minus infinity to plus infinity x of k e power j k omega naught t. Okay, so this is equation number 1 there. So I have the continuous time signal, that is x of t. So how I can represent it? So I am representing it by sigma k is equal to minus infinity to plus infinity x of k, okay, e power j into k omega naught t. Okay, so this is the complex exponential that is there. This is the complex exponential. This is the complex exponential. So now you would be like thinking whether x of k, which is there, how it is being represented. So as I already told you, x of t, this is the continuous time signal. So this x of k is referring to a complex Fourier coefficient. Complex Fourier coefficient. Okay, so complex Fourier coefficient. Okay, so this is the complex exponential. So this one is the complex Fourier coefficient. Okay, so now this x of k is represented as 1 divided by t integral t, which is, I'll tell you integral t, how did I write it? X of t e power minus j k omega naught t dt, which is equation number 2. Okay, so this is x of k here, which is written as 1 by t integral. Okay, so integral. Okay, so x of t into e power minus j k omega naught t dt. Okay, so this integration which is there, which is performed over a period. Okay, so integration is performed over a period. Okay, so this integration, whatever that is there, so which means that it is being performed over one complete period. Okay, so now it can be analyzed, any periodic waveform can be analyzed or realized quite easily with the sum of the exponential. So this equation 1 is called as the synthesis equation. And the equation number 2, this is the analysis equation. This is the analysis equation. Okay, so as I already told you, x of k is called the complex Fourier coefficient. Complex Fourier coefficient. Okay, so now x of k, okay, x of k, when it is x of 0, okay, so this one is called as the DC term. Okay, DC term or the average value of the waveform. Okay, please remember this equation what I've written there. So this is x of t, which will be called as the synthesis equation, and this one is called as the analysis equation, that is x of k. And this x of k, once you have k value which will be equal to 0, it will be called as the dc term, or the average value of the waveform. So this x of k is called as the complex Fourier coefficients. Okay, so this is called as the complex Fourier coefficients. Okay, so it can be written quite simply like x of t, x of t, you can find out x of k. Okay, so x of k using the Fourier series. Okay, so this is the Fourier series, that is x of t being the periodic, so x of k being the complex Fourier coefficients, it can be analyzed. So this periodic waveform and its Fourier coefficients, that is x of k, can be analyzed. Okay, so when I'm talking about Fourier series here, it should be a continuous time signal, that is x of t, and fs, that is the continuous time Fourier series, that needs to be analyzed here. Okay, so just before I move to the next concept, okay, so I'll be talking about orthogonality of complex sinusoidal signals. Okay, so I'll be taking help of the orthogonality. These are just formulae that you need to remember. So once you have a given wave, so you need to analyze its Fourier series quite easily. Okay, so orthogonality of complex sinusoidal signals, there. Okay, so whatever that I'm going to analyze here, so that would be in terms of the continuous time signal, that is x of t and y of t there. Okay, so x of t and y of t, I'm going to analyze it, and I'm going to realize the complex sinusoidal signals that are there. So when I say it is a complex sinusoidal signals, okay, so its conjugate will also come into picture, right? So and later on you will be having the continuous time signal, which is also there. Okay, so x of t and y of t. Okay, so let us talk about this one. So we have x of t and y of t being the weighted superposition of complex sinusoids. Okay, so I have x of t and y of t here. Okay, so I need to evaluate it over the interval, that is a and b. So this is the interval that I need to evaluate. Okay, so now what do I need to do? I need to evaluate over integral a and b. So x of t, okay, and I'll be having y star of t. Okay, so I need to prove this to be the, or to prove the orthogonality of the complex sinusoidal signals there. Okay, so integral a to b x of t and y star of t, that would be equal to 0 then, right? So now I have a signal called as x of t here. Okay, so this one, okay, I can write it like this. I'm taking a simple example just to make you understand. Okay, so I have a signal, okay, that is x of t, that is from the period, that is 1, 2, 3, and 4. Okay, so from 0 to 4 I have it. So 0, this is 1, this is 2, okay, this is 3, and this is 4. Okay, so that is that. So I have signal 1 and signal 2, both are continuous time signals there. Okay, so I'll be able to evaluate this integral, that is from a to b, x of t and y star of t. Okay, so y star of t, that is nothing but the complex conjugate, okay, of y of t. Okay, so y star of t is nothing but the complex conjugate of y of t. I'm taking this as an example to prove the orthogonality of the complex sinusoidal signals there. Okay, so let us proceed here. Okay, so let us check over the interval whether it is orthogonal or not. So as I already told you, I need to evaluate it from integral 0 to 4, that is x of t and y of t, that is to be multiplied. Okay, so x of t and y of t. So how do I do do this. Okay, so x of t and y of t, if I want to see, so the value of a would be equal to 0. There limits what I'm talking. So a and b would be 0 and 4 respectively, right? So now x of t and y of t, so that would be from 0 to 1. Okay, so what is its value from 0 to 1 if I need to take x of t and y of t? Okay, so I have taken here as y of t, that is y star of t, sorry. So that would be like y of t, if I need to take it, that would be the real part of the y star of t. Okay, real part of y star of t. Why it is real part of y star of t? Can anyone tell me? Okay, can anyone tell me why did I write it as integral a to b x of t into y of t? Okay, so this y of t, y star of t in the given waveform, it is considered to be the real part of y of t. Okay, so there is no imaginary part which is being present there, and that's the reason why I am taking this y of t in the integral over here. Okay, so let me analyze it from 1 to 2. Okay, next from 2 to 3 plus integral 3 to 4. Okay, that is there. Okay, so integral 0 to 1. So I am talking about this product of these two signals which are there. Okay, so let me analyze it from 0 to 1. Okay, so let me analyze it from 0 to 1. This is 1, this is minus 1 which is there, this is 1, and this is minus 1 there. Okay, so 0 to 1. Okay, so I have 1, 0 to 1, 1. So its value would be equal to 1 there. Okay, so let me analyze this with respect to a waveform also here. X of t into y of t, that is the product. Okay, so that would be 0 to 1, that is 1. Next 1 to 2, I have it as minus 1. Okay, so why I'm writing this as a straight line is, so from 0 to 1 it is there, and this is 2. Okay, so it is minus 1 there. Okay, this is 1. Okay, so this one is like this. Okay, so this is 3 and this is 4. Fine, so this is minus 1 and this is 1 and this is minus 1. Okay, so if you evaluate this integral, what would be the evaluation of this integral? This is 1 minus 0 plus with a minus sign, that is 2 minus 1 plus 3 minus 2. Okay, plus 4 minus 3 with a negative sign. Okay, so 1, 2 minus 1, that is 1, that is minus 1. This 2 get cancelled, plus 3 minus 2, that is 1, plus this is 4 minus 3, that is minus 1, that is equal to 0 then. Okay, so we can evaluate and we can say it over any integral. Okay, that's been evaluated over the interval a to b, x of t and y star of t, that would be equal to 0. So hence orthogonality of the signal is valid. Okay, so this orthogonality of signal is being valid. Okay, so that is where you can find out, and I'll be discussing more about the orthogonality of the complex exponentials over the derivation also, and later on I'll be considering the derivation of the complex coefficients of exponential Fourier series. Okay, so this terms, whatever that is there, these are nothing but the derivation aspects of the complex Fourier series. So there will be a lot of derivations which are there, and few problems which you need to analyze it, and then we have to find out whether the given complex Fourier coefficient, okay, complex Fourier coefficients has to be analyzed there. Okay, so with this note, I would like to okay, so with this note, I would like to end today's session. Okay, so I want you to go through it, whatever that we had discussed. If you have new things which have to be discussed, okay, so we'll discuss certain things in detail there. Okay, so with this note, I would like to end today's session quite easily. Okay, so it would be useful for you to understand it. Okay, thank you everyone.